Okay, so today we're going to talk about 2.2 separable equations. In chapter 1, we discussed some terminologies, some definitions. That's a brief introduction of the different equations and initial value problems. Okay, if you have initial conditions added to the problem, then it's called initial value problem. In addition to the differential equation, but we never had a chance to actually solve a differential equation. We did check or verify some solutions for differential equations, but we never discussed how to solve those equations. So starting from chapter 2, we're going to talk about those methods in the whole course. And we started from the very simple case of separable equations. That means you can separate the variables and integrate. Okay. So typically a separable equation is the equation of dy over dx equals 2gx times hy for the first order differential equations. So you can see on the right hand side, we have two functions, g and h. They are functions of x and y respectively. So these two variables can be separated in this case. Then what you can do, you can divide by gx and hy on both sides, and then multiply dx. So you're going to get a dy over hy equals dx over gx. Okay. So remember, dx, dy are differentials. So on the left hand side, you only have variable y, and on the right hand side, you only have variable x. Okay. So then you can integrate on both sides of the equation simultaneously to solve this equation. All right. So that's called a separable equation because you can separate the two variables in this equation. So let's just do some simple examples. Suppose we have a differential equation dy over dx plus 2xy squared equal to 0. So this will be a separable equation if you move 2xy squared to the right. So it becomes dy over dx equals negative 2xy squared. So you can see on the right hand side, you get x, y separated. Okay. Or you can separate these two variables. Okay. So what you do, you can divide by y squared and multiply dx on both sides to get dy over y squared equal to negative 2xy squared, negative 2x dx. So then you just integrate on both sides. Okay. So on the left hand side, you can rewrite the whole thing as y negative 2 dy for the integral because y squared is in the denominator, remember? So that's the negative exponent. And on the right hand side, you just integrate x over x or 2x directly. So you just use the power rule, on both sides. On the left hand side, you just add 1 to the exponent and then divide by negative 2 plus 1. That's the power rule for integration, remember? On the right hand side, you just use the power rule again, So that's 1 plus 1 for the exponent, and then you divide by 1 plus 1. All right. So on the left-hand side, it becomes y to the -1 over -1. So that's just negative y to the -1. On the right-hand side, you just get the negative x squared. Remember, -2 and 2 in the denominator, just cancel the 2. Plus c, all right? So we can actually write the solution explicitly if you rewrite y to -1 as 1 over y on the left-hand side. So then that's 1 over y equals negative x squared plus c. And then you just multiply -1 on both sides. You get 1 over y equal to x squared minus c. So everything changes to the negative sign. And then you flip it on both sides. So you're going to get y equals 1 over x squared minus c. So that will be the solution to the differential equation. Okay. Or a solution to the differential equation, actually. Now, one thing to be noted is that the problem or the differential equation also has a constant function solution y equal to 0. Okay, if you look at the original differential equation, dy over dx plus 2xy squared, and you plug in y equal to 0, the constant function. Since the derivative of constant, then the function is 0, so you get dy over dx equal to 0, and also y equal to 0, so 2xy y squared equal to 0. So again, everything on the left is 0. So the equation is satisfied with this constant function y equal to 0. So that means y equal to 0 is also a solution to the differential equation. I think we discussed it before in 1.3. But in this process of solving the differential equation, we just lost it. Okay. We got one solution, y equal to 1 over x squared minus c, but the problem or the equation also has another solution, y equal to 0. And the solution is lost during the process of solving the equation using the separable equations. And the reason is we divided by y squared on both sides of the equation, okay? So that inhibits y equal to 0. Okay, so when you divide by y squared on both sides of the equation, that automatically means y cannot be 0. So that solution was excluded in the process. Okay, but the problem does have another solution of y equal to 0. All right, so we need to be very, very careful, when we divide by anything on the equation. You can potentially or possibly miss some solutions. Okay. And this y equal to 0, the constant function solution, is also called the singular solution. Okay. Any questions for this simple example? We know a differential equation can have multiple solutions. It's not unique sometimes, as we discussed the theorem in 1.3. And sometimes you can miss the solution when you use some procedure. And this is very typical when you solve some other solutions, for example. Right? Yeah, that can also happen in any algebraic equations. So if no question about the example, then we go to the next page. So let's just do one more example. This time we need to solve the initial value problem. That means we have a differential equation plus the initial condition. So the equation itself is dy over dx equal to negative x over y. And the initial condition is y of 4 equal to negative 3. Okay. So we need to solve the equation first. When we do that, we're going to have a solution with some arbitrary constant c. And that arbitrary constant c will be determined by the initial condition in the problem. Okay. And again, this is a separable equation. If you rewrite the equation by multiplying y and dx on both sides. Okay. So what you get will be y dy equal to negative x dx. So again, the variables x, y are separated on the two sides of the equation that you can integrate on both sides simultaneously. And this is an easy integral. We know how to do that. So on the left-hand side, you can rewrite y to the 1 dy. On the right-hand side, you can write to the negative integral x1 dx, and just use the power rule to integrate. So on the left-hand side, you get y to the 1 plus 1 over 1 plus 1. That's the power rule. And on the right side, you get the negative x to the 1 plus 1 over 1 plus 1 and plus c. So the whole thing just becomes y squared over 2 on the left and the negative x squared over 2 plus c on the right. If you simplify it and if you want to get rid of the fractions, you just multiply by 2 on both sides of the equation. So then you're going to get the y squared equal to negative x squared plus 2c. Okay. Multiply each term by 2. But you can also move negative x squared to the left. And that becomes positive. So the whole thing just becomes x squared plus y squared equal to 2c. But c is just an arbitrary constant that you can rewrite as c1. Okay. So then we end up with the solution of the differential equation with some arbitrary constant c1 that can be determined by the initial condition, which is y of 4 equal to negative 3. So the initial condition means when x equal to 4, y equal to negative 3. So what you do, just multiply 4 for x and y to negative 3, and the equation or the solution should be satisfied. So then we get a 4 plus square plus negative 3 square equal to c1. And 4 square is 16, negative 3 square is 9, so we got 25. So c1 equals 25. So then the solution to the initial value problem is just x squared plus y squared equal to 25. Okay. So we determine the arbitrary constant c1. And if you draw the graph of this function, you're going to see there's a circle centered at the origin with the radius 5. The solution x squared plus y squared equals 25. One thing to be cautious is the derivative does not exist at the left and the right end points of the circle at x equal to 5 or negative 5. So if you draw the circle, you see there are 2 vertical tangents at the left and the right ends. So that means this relation x squared plus y squared equal to 25 is not continuous. But we require, the function to be continuous because you are taking the derivative of this this y. Okay. So the derivative has to be existing. That means the function must be continuous. Okay. So what it means is we have to take out the two endpoints of the circle on the left and the right. Okay, so that will divide the graph into two parts. So one part on the upper half plane and the one part on the lower half plane. So there are two branches of the solution. All right, which is separated. Okay. So that means the solution is either the upper half curve or the lower half curve. Okay. We only consider a continuous curve as the solution. Well, if you consider the initial condition, y 4 equals to -3, that means x equal to 4 and y equal to -3. So if we plot that point, it is on the lower half plane, the point of 4, -3. So that means the solution is actually the lower half curve, okay, which passes the initial point of 4, -3. Okay, then we can rewrite the solution of this initial value problem as x squared plus y squared equal to 25, where x is greater than -5 and less than 5. Okay, y is greater than equal to -5, less than 0. So that's lower half curve. Does it make sense? Any questions about this example? I'm going to stop here. Stop share now. Stop the recording also.